Okay, apologies if I cough and splutter a little bit through this. We have been looking at the various models for the atom that were introduced from 1900 on to about 1920, when physicists were trying to understand what was going on and interpret their results. You remember we talked about Rutherford's solar system model of the atom, and then Bohr's model of the atom, where the orbitals were quantized. They had to be in fixed positions, fixed energies. And we've talked about the standing wave condition, which is where we take de Broglie's idea that electrons can have wave-like behaviors. I should have put an N in that can. That electrons have wave-like behaviors, and that if electrons have wave-like behaviors, then we can envisage the quantization Bohr talked about in terms of a standing wave, as in whole numbers of wavelengths of these de Broglie wavelengths that are associated with the electron fitting onto the various orbitals. And this yields what's called a semi-classical model. So it's not fully yet quantum mechanics, because we're still really sort of thinking about the electron as a marble doing circles, but we're starting to put in some quantum mechanical ideas, such as the wave nature of the electron, and the idea that the electron, as it goes around its orbital, is doing superposition, and there's only certain orbitals where that superposition is constructive, and it's those orbitals which exist. Anyway, the standing wave condition, when it's applied to the orbital mechanics, which is exactly the same orbital mechanics that we'll do with the solar system, and satellites in Earth orbit later on in the course, when we apply the standing wave condition to those numbers, we get exact answers for the size and energy of each allowed orbital for hydrogen. And this gave us an expression, which is where we finished last lesson, which tells us that the energy that an electron essentially gains, the reduction in the electron's energy because it's been bound into the atom, is given by 13.6 over n squared EV. And it's got a minus sign because we would get energy out. If the electron joined the atom, we would get energy out, and we follow the same convention as the chemists do, which says that when energy comes out of a system, we give that a minus sign. And it's in EV because we're doing particle physics. It's all in EV. It's all in electron volts. We could convert it into joules, but usually those values are given to you in electron volts. And n there, of course, is which orbital. Those numbers down the side of the periodic table, 1, 2, 3, 4, the various periods, that's n. Now, chemists, as I mentioned in the lesson, the chemists don't bother talking about the fact that hydrogen has all the higher orbitals as well, because for a chemist, they're only interested in filling the bottommost orbital. But we know that actually all those orbitals are there for hydrogen in the same way they are for everything else. And so hydrogen doesn't have to go into the bottommost orbital. It can go into any of them, hence the expression. Now, you're perhaps looking at that worrying that you're going to have to use that expression or remember that expression, but you don't. What you get is energy level diagrams. So this is sort of going to be an energy level diagram. It's not unlike the energy level diagrams that we've already touched upon on the course. I drew an energy level diagram when we were talking about the electrons bound inside metal, and the photoelectric effect, and how deep the electrons were within the metal's potential well. I drew a diagram not too unlike this, and I drew some diagrams not unlike this when I was talking about semiconductors and how LEDs work. The difference there is that within solids, there are so many overlapping orbitals that we treat the energies as being falling within bands. The electrons could be anywhere within the band. But when we're talking about a single atom, the electrons are only very particular values. Now, the dotted line there sort of represents an electron that's free, that's not part of our atom. So its binding energy would be 0 eV, not yet bound to our atom. And that's also the most infinite energy level, because if you look at the expression there, if n goes to infinity, then E falls to 0. So that could the vacuum level, the 0 level, could also be regarded as the infinite energy level. But saying that's quite hard. Of course, most of the time, our electron is going to be right in the bottom of this potential well again. It's going to be sitting at minus 13.6 eV below 3, what's known as the ground state, n equals 1. But as I mentioned in the previous slide, the other orbitals are available. If you're a chemist, you know that the other orbitals are more complicated. There are suborbitals and things, but they're all at roughly the same energy. They are what's called degenerate, have the same energy. So we know, well, because this is an energy level diagram, we don't care about all of that. We just care about what their energies are. So there's n equals 2. So all I've done is taken 13.6 and I've divided it by 4. And n equals 3, I've taken 13.6 and I've divided it by 9. And n equals 4, I've taken 13.6 and I've divided it by 16. And you can see that I could carry on doing that forever, but they're all going to get very close together, and I'm not actually going to be able to mark the values in after that. I could keep on going, but they're going to get so close together I can't actually mark the values in. So that's the energy level diagram that you're likely to see in an exam question about this stuff. Typically, the examiner uses hydrogen because it's more complicated for anything else, because anything else has got more than one electron in there. So typically the examiner uses hydrogen. The only thing that the examiner can do to confuse this, really, to make it more complicated, is not to give you the energy in electron volts, but to give you the energy in joules. So somewhere there'll be a energy in joules times 10 to the minus 18 showing up somewhere, and if that's the case, then the ground state is minus 22, if I remember rightly. 13.6 multiplied by 1.6 times 10 to the minus 19, minus 22 times 10 to the minus 18. So look out for that. If there's a 22 in there, then you've been given the energies in joules and not electron volts, but usually you're given it in electron volts. Okay, so our electron tends to sit in the ground state, tends to sit in n equals 1, tends to sit at the bottom of the potential well. That's where a chemist always imagines it sits. I've drawn our electron as a circle. If you're a chemist, you're probably used to doing it as a sort of half arrow, and we'll talk about that a bit more probably later on in the course. But for now, a dot's going to do for my electron sitting in ground state, sitting in n equals 1, sitting at the lowest possible energy it can manage. Now, something promotes it to n equals 2. We'll worry about what the something is a bit later on when I'm back. But something promotes it to n equals 2. It gets some energy from somewhere, probably a collision. Ends up in our electron ends up being promoted to a higher energy level. So we refer to the atom as being excited because it's no longer sitting in its ground state. It's excited. It's got a bit more energy than it should have. So our electron's now in n equals 2. Now, of course, our electron wants to get back to ground state. Of course it does, because that's its lowest possible potential energy, and things have this tendency to want to sit in their lowest possible potential energy. The analogy I use all the time is, a rock on top of a mountain is eventually going to end up at the bottom of the mountain. It wants to get to its lowest possible potential energy, and it's the same with our electron. It is going to transition back to that ground state from n equals 2 to n equals 1. But of course, in order to do that, it's got to get rid of some energy. How is it going to get rid of that energy? Well, there's only one mechanism available to it, and that's to fire out a photon. So in transitioning from n equals 2 to n equals 1, our electron is going to fire out a photon, and of course that photon is going to have a very particular energy. It's going to have an energy given by the difference between those two energy levels. It's going to fire out a photon with an energy of 10.2 electron volts. And of course, if the photon's got a very particular energy, we know from Einstein, E equals hf, that Our photon energy means that it's got a very particular frequency, and if it's got a very particular frequency, then it's got a very particular wavelength. So basically that transition from n equals 2 to n equals 1, if we're talking about hydrogen, can only result in photons of one very, very particular energy, one very particular wavelength, effectively one very particular colour. And basically that's the basis of atomic spectrum. Okay, so an energy a question in an exam might read something like this. So you've got that energy level diagram on my previous page, and you have been asked to calculate the wavelength of a photon emitted when the electron in hydrogen drops from n equals 2 to n equals 1. And you're asked what part of the spectrum would this photon be in. Okay, so it should be straightforward for you guys. So already on the previous page, we've said that we're transitioning from 3.41 to 13.6, which gives us an energy in the transition of 10.2 eV. The examiners don't tend to be very bothered about the minus signs in there, so if you don't worry about all those minus signs, if you just say 13.6 subtract 3.41 ends up at 10.2, you'll get the marks. Now, of course, we can't do any calculations in electron volts. We've straight away, first job is always to convert electron volts back into joules, which is a simple matter multiplied by 1.6 times 10 to the minus 19. Gives me a photon energy of 1.63 times 10 to the minus 18 joules. And then we just got to reach for our equation. We could use E equals HF, but if you've been asked for wavelength, better off to use the equation that actually contains wavelength, E equals HC over lambda. Rearranged, we get lambda is equal to HC over E. I've slotted all my numbers in there, bung that in my calculator, and I come out with 1.22 times 10 to the minus 7. Of course, 1.242 times 10 to the minus 7 meters. And you know I like nanometers, so I've converted that into 122 nanometers. And you should know where that falls in the spectrum. You should know that the ultraviolet occurs below something like 400 nanometers, something like 390 I think it actually is. We did that calculation when we did the spectrum practical. You know that if that's below 390 nanometers, then that must be ultraviolet light. So 122 nanometers is ultraviolet radiation. So there you go, we've answered the question. But the more interesting thing is if you look back at that energy level diagram, and I'm going to put it on again in the next slide, if you look back at that energy level diagram, n equals 2 to n equals 1 is the smallest possible drop that ends up at ground state. Because n equals 3 to n equals 1, or n equals 4 to n equals 1, or n equals 5 to n equals 1, they're all bigger. That means they've got more energy. And if they've got more energy, that means they're even deeper into the ultraviolet. And so all of the possible transitions to ground state within hydrogen always result in ultraviolet photons. So we can't see, we can't see hydrogen transitioning to n equals 1. And I hope you can see what I mean now. I'll put the diagram back up there. I drop from n equals 3 to n equals 1. That's a bigger drop. That's a higher energy. That means a shorter wavelength. That means deeper into the ultraviolet. The same for n equals 4, same for n equals 5. And it turns out it's the transitions to n equals 2 within hydrogen which produce visible light and produce photons that are visible to our eyes. So if we were to get a drop from n equals 3 to n equals 2, not that likely an event, to be honest, but if we were to get a drop from n equals 3 to n equals 2, then that would produce a photon in the red. And if we were to get a drop from n equals 4 to n equals 2, then that would produce a photon that was green-blue. I've got green-blue, so that's blue. Or if we were to get a drop from n equals 4, then we're starting to get up into the violet. And again, I haven't got violet, that's purple. And so those three different possible wavelengths of photons that can be emitted from hydrogen, because they're in the visible spectrum, are incredibly important to astronomers, in that, sorry, brain stopped. In that most astronomy takes part in the visible part of the region, because it's the visible part of the spectrum that comes through the atmosphere, and most of the universe is made out of hydrogen. So if you're looking for hydrogen, you're looking for those three different photons of light, either being absorbed or being emitted. And so they form the visible spectrum of hydrogen. And I showed you that with our spectrometer the other day. I showed you those three peaks in a hydrogen discharge tube. The three different bits of light, frequencies of light, wavelengths of light that are associated with the visible part of the hydrogen spectrum. So they're really, really important, and therefore they have names. So in astronomy, they're called H alpha, H beta, and H gamma, because that's A, B, C in the Greek alphabet. So they're really important, and because they're important, they also turn up to be the most common answers to exam questions. So, you know, when you're asked to calculate what's the wavelength associated with a photon emitted by this drop, this transition, you're unlikely actually to get asked for the one that we've already done, n equals 2 to n equals 1, because that's not the important one. You're more likely to get asked for n equals 3 to n equals 2, because that one's the important one, H alpha. In fact, you're asked to calculate it so often when you're doing past exam questions that you start to recognise the wavelength, because you have to calculate it so much. So because I'm not in, and you need to have something to do, and this has not taken up an entire lesson, then can you please calculate the wavelengths of each of H alpha, H beta, and H gamma before the next lesson, which probably means you're going to need to pause this video and write down the numbers for n equals 4, n equals 3, n equals 2, and n equals 1 so that you can sit and do the calculations. They're fairly repetitive calculations, but hopefully you'll come up with nice values for the wavelengths for each. No cheating and going away and looking at what they actually are until you've done the calculation. By all means, go off and look up what they actually are once you've done the calculation to check that you've got it right. But do the calculations by yourselves first. So if you could get that done before I see you again, or rather before I create another video, then I would be very grateful. And I'm going to try now and put together another video for your lesson tomorrow morning. How successful I'll be, I don't know, but I'm going to give it a go. So that will do for now, and hopefully I'll see you in lessons before too much longer.